like, so that everybody wakes up. That's a Fandango party near where I live in California, in San Jose. So these are just our neighbors. Okay, so I've been working on like category theory implementations for I don't know how many years. This is kind of relatively new implementation in Scala, and the purpose was to investigate like what logic can we have in different toposes, and to really like produce some results. Actually, there are some results I published like eons ago. So Scala was like a little bit challenging. On one hand, we have, like in Java, I have a Java implementation. So I had those like type parameters, like category with node type or object type and arrow type. In Scala, eventually, I kicked them out and I made them just members of the class. So this is how category looks like. We have a name. Name is just good for like, printing like here and there. So we have a type of objects, well, because it's a graph, and in graphs, objects are called nodes. And we have arrows, identity. Well, what does a category need? Like identity and the composition. The composition is a partial operation. So first, second, and this is the composition. So this is an abstract class, right? To create an op category where arrows are like inverted, you do just this. So it's the same category, but identity is this way, and composition is the opposite direction. And actually, there's, well, that's, yeah, it should be like in the opposite direction. And there should be more. The name is like tilde, right? So there should be more. D0 and D1 should be replaced. Yes?
So as a parsing function, does it throw an exception?
No, it returns an option, so it doesn't throw an exception, yeah. Yes, basically, I wouldn't say I use option much in this code, but it was like kind of convenient to use option specifically in this case. So, but now I use graph, right? So what is a graph? A graph is something that has a type of nodes, a type of arrows, and a set of nodes. When I say set, like when a mathematician talks about the set category, you can always ask, like, what is it based on, and so on, like turtles all the way down. So it's a set. Here we have we deal with a Scala set, but not exactly. And we have domain and codomain of each arrow. So that's it. That's all you need for graphs. Except that if you build it, you also like you are provided with nodes, arrows, and you have to check that it's all compatible. So I had to introduce sets that are closer to mathematical sets. And in math, in set theory, sets don't have types. So I introduced this type, set, just any there. And if I have a set like which I get from somewhere, and I want to convert it into this, like my small set, I write like dot untyped. And so further down, the code doesn't care about like what was inside. They're all like sets to it. Like objects, anything, any. So for a set, like we can check if a set is finite. And this is a Java libraries check, which is like max value is the signal that the set is infinite. And we have an empty set, a constant, and we have a constant called unit. Of course, there's more than one unit set, singleton set in set theory. There are exactly the same number of singletons as sets, right? Because like for any set, you can build a singleton. So, and we have a set of finite sets, which we just take all possible sets and choose those that are finite. So this is how big set is defined. Like, what else? But basically, because we are there, we have to make sure that we don't enumerate like the set of all sets and so on. So that's why I have this trait, non-enumerable set. It will crash if you try to check, is it empty? If you try to iterate, If you try to convert it to array, no, it will crash. That's something that doesn't belong to sets. That belongs to enumerable sets. So if you study like constructive theory of sets, whatever, so you will see that there is a difference. So I had to like throw in this difference and deal with not enumerable sets, but at the time I deal with enumerable sets. Why did I have to do it? Well, because then I can deal with really like bigger sets without trying to enumerate. Well, because it's JVM, it's Scala, so every time you write something, suddenly, oops, it starts like listing all elements. How can you list all like real numbers? How can you list all sets? No, it's impossible. So I have this like guard trait that like kills all those attempts, and it will throw stones at those that try it. So, okay, that was a preamble. So I'm sure everybody here is already familiar with categories, right? So everybody knows the category of sets. Everybody knows the category of Haskell with pure functions, another Haskell with partial functions, Haskell which is actually a Kleisli category over the monad of partial functions, and so on. Scala is some kind of a category, Scala with arrows that are inheritance, like from one type to another, that's another category. That's what you use when you define like this type is a subtype of that. So that's a different category from like regular Scala, with map being done by just functions or methods or whatever. Any type class, well, this is like arguable. So some people say that a type class is a functor or functor is a type class. No, I think a type class is just a category. And there are more categories, right? So like small samples of small categories are here. Category 0, you saw it already on the first slide. Just an empty category. In my code, it looks like this. It's a category, and it's a segment with like 0 elements. Category 1, this is the official notation, and it consists of just one object, and it's a segment. So category 1 plus 1 consists of just 2 objects and no non-trivial arrows, so it's called 1 plus 1, and it's a discrete category on this set. Category 2, well, it's a segment consisting of 0 and 1. Category 3 is a segment consisting of 0, 1, and 2. And we can throw in more, like category 4, it's a segment of 4. Now to define it like, to be more flexible in defining a category, there is this, some kind of DSL. Scala, thank you, Scala, it had this macros where you can define things. So this is a macro that says like category, and you define this category, and it will build this category. So a parallel pair category. 2 objects, 4 arrows, A and B, and we have this, like we define arrows. Pullback, why is it called pullback? Because we can build pullbacks out of this category with 3 objects. So it's a pullback with 2 arrows. And non-trivial, trivial arrows are being built by a constructor when you define it. And category square, now we had to define a composition. So here we say AB followed by BD is equal to AD, and AC followed by CD is also equal to AD. And because it's a DSL, so when it tries to build it, it also checks like everything, check the associativity, check the identity composes correctly, and so on. And that all compositions are defined. And if they are not defined, we try to find out. So basically, actually, if you don't even define like a composition of CD with AC, it will figure out like there's no other option, no other arrow. But it's pretty easy, right? Anybody can find that. So this is the category that is defined in this DSL like this. And if you write to string on this category, it will produce exactly this without the word category. So there are bigger categories, and we can define bigger categories here. A category of natural numbers. It's built from partial order of natural numbers. So I have this like, thank you, Scala. We can use like any Unicode, well, almost any Unicode character. So it's like that official N for natural numbers. So it's a partial order of natural numbers. And what's a partial order? It's we give a set and we provide a comparator. So we have a partial order. That's it, right? And when we build the category, we check that like it's all legit. Well, for partial orders, it's always legit, right? And what is like the set of all natural numbers. Like you cannot materialize it in Scala, right? Or in Java. But it's enumerable. At least it's enumerable, right? And the iterator just produces what? Like 0, 1, and so on. And how do we check that it contains a number? We just check that that number is like non-negative. That's it. So that's a set of all natural numbers. Maybe we will never reach like very big numbers before like the computer like dissolves in the universe, with the universe. But anyway, it's something like doable, but never materialize the whole set, right? And also there's an even bigger category. Set category built on a given set. So we can build even the set of the category of all sets. So we build a graph of all sets. Well, how is it? It's kind of obvious, right? Given two sets, like if there is a function, so that function gives us an arrow. So what do we have? Type node is set. Remember that like typeless set. Type arrow is set function. I'll show you on the next line what set function is. Well, because we have function, right? You can define a function. The problem is our functions in Scala, in Java, and like everywhere, in Haskell, I believe, they don't even mention domain and codomain, which is a little bit weird from categorical point of view. So I had to define. And so for a set function, we define like D0, the domain is just D0 of that function, D1. Composition is like this. F compose F. Well, we have to define that compose, right? Identity is kind of obvious, and toString is just this. And set F is the set category of all finite sets. I already showed you what finite sets are. So basically, I'll be handling, when I build diagrams or functors, those functors will be into set F, the set of all finite sets. So what's a set function? It's like a function, like have a mapping, but also it mentions like what's the domain and what's the codomain. And so if we define a function that like adds 1 to natural numbers, and if you don't say that we define it on natural numbers, so we don't know what function it is. So we need to provide the domain. Otherwise, how do we compose, right? So that's how it is. And composition is defined obviously. We just compose like our function with the next one. So this is pretty trivial. The only thing is that we have to check the domain. And also, we check that, if it's equal, so we can compose, and we produce this new function. Otherwise, it's none, no. Like, it doesn't compose. But morphism in general, so set function is a kind of morphism. Setmorphism is a kind of morphism. And setmorphism is like a little bit more abstract thing than just this case class. So what does morphism consist of? It has domain and codomain. It doesn't know anything about composition. Why? Because this thing could participate in different categories. So we have this category. Composition, generally speaking, is defined by a category, not by this like small thing that like just knows its domain and codomain. So that's why. So a functor, I'm not like defining anything like from categorical point of view because, well, I believe everybody knows it already, right? So a functor is just a morphism from one category to another. So domain is category and codomain is a category. And how do we define a functor? We have to specify how objects are mapped and how arrows are mapped. So we need object mapping and we need arrow mapping. So we need these methods, two functions, and they produce us they give us the whole definition of a functor. And a composition, yeah, we can define compose for functors because we know how functors compose. So if the domain is not the right, if the domain and codomain don't match, so we have none. Otherwise, we just compose these two functions. That's it. Like this object goes to that object, and that object goes to that object. The same with arrows. So like no trick. We compose them as if they're just plain functions. So that's a functor. Generally speaking, not a functor like that we define like in types. So usually like in Scala, in Haskell, and whatever, in Java, in PHP, functors, the only category we are talking about is one specific category of like types or whatever. So no, this is a general function. A category like could be any category, could be empty, could be category of all sets, or could be Scala. So a specific kind of functor is a constant functor. So given a category C and a category D and an object in category D, we produce a functor. That functor gives what? That functor takes any object from C and gives us that Y. That functor takes like any morphism in C, any arrow, and gives us an identity on Y. So it's defined like this. We have the first category, like X and Y, and a point, a value, an object Y0 in category Y. And it's a functor, and I say build, meaning that usually like in this code, when you build something, build a functor, you like validate everything, like is it correct, is it compatible, and so on. But if we know that const is like pretty trivial, right? So we cannot break the rules. So it's an unsafe build of a functor from X to Y. We just trust our theory. And it gives us like a constant functor on objects producing Y0 and a constant functor on arrows providing identity on Y0. So that's it. So that's a functor, like a primitive example of functor. And so unsafe build, like we have a domain category, codomain category, and we have to provide object morphism, arrow morphism. And what's interesting, like we have to use path-dependent types. It's like a Scala solution for dependent types. If you're a Haskell person, like it could look a little bit weird probably, but I don't know. But in Scala, it's called path-dependent because like you have an instance, but it's complicated. And it doesn't always work, but later. So object morphism would be from objects on domain category to object on codomain category. And arrow morphism is a mapping from arrows on domain category to arrows on codomain category. And a category is like just an instance of that thing that I showed you on slide number 3. So okay, functor. Now, if we have two functors, we can build like an arrow from one functor to another and have the whole category of like functors between one category and another. So it's a consistent mapping from one functor to another. Like usually they use Greek, small Greek characters like alpha is a natural transformation from functor f to functor g, where functor f and functor g are two functors from category x to category y. So it's defined by object-wise mappings. Like for for object C, we need something like an arrow from FC to GC. For D, we need an arrow from FD to GD. For B, we need an arrow from FB to GB, and so on, for every object in category X. So that's why natural transformation is defined as a morphism from a functor to a functor. Like, I enjoy the fact that I don't need to provide those parameters. In like Java version, I had to like 8 lines specifying like parameters of parameters of parameters, and they don't even make any sense because it's Java, JVM, and type erasure. So here they're inside. So the domain for this morphism would be what? It's a category, this category, right? Codomain. Well, no, the domain of the morphism is, of course, F, and codomain is G, but we also need to say, like, what category we are talking about. So the category is D0. D0 is what? Is a functor, and that functor D0 is that category from which that functor is. And the codomain is, like, where we go, this Y. And the problem is this should be equal to D1.0, and this should be equal to D0 D1. And there's no way to check this case, except that, well, we can try to like validate, but it's a little bit problematic. And again, if it's a type, so it could be a problem. So, but anyway, like enough about problems. What we need to provide is a transformation from one functor, like the value of a functor on each object. So we need an arrow in codomain category in Y for every object in domain category in X. So that's what we provide, an arrow there. And what that arrow, we don't know. if we are talking about like this category, it could be just like anything, anything that we invent. So an arrow is not a function. An arrow is like an abstract thing. So that's why it's just like a totally arbitrary type. So let's keep those cones and limits. Let's get to diagrams. Anybody familiar with what presheaves is? Yeah, okay, so I'm not going to presheaves, so like a warning. I don't like presheaves, I like diagrams. And what's a presheave? It's a diagram with like op over this domain category. So I'll be talking about diagrams. It's easier to program. You don't like get switched and opt all the time. So there will be like diagrams all the way down. So a diagram of a category C in category D is a functor from C to D. That's it. Have two categories. A functor is a diagram, except that we don't talk about diagrams if category D is like something trivial, small, primitive. No, usually diagrams are into sets or into like other toposes, like finite sets. So this is a picture of a diagram. We have a category C, like in this case, 3 objects and 2 arrows. And this is category sets. And for this diagram, we define like f of b. We define a diagram f. So we need f of b, f of c, f of d, and 2 arrows. And the notation is more or less like Scala style with square brackets instead of parentheses. I find it like pretty convenient, like stealing this notation from Scala, although we are not talking about Scala. It's just a notation. So have a category of sets and have a category C. This mapping, this functor, is called the diagram just because it's a functor. That's it. And this D doesn't have to be sets or like finite sets, anything. But we'll be talking about sets because the sets have a lot of like interesting features. So toposes, or like at least Grothendieck toposes, consists of diagrams or presheaves. We will have a presheave if instead of category C, we'll have category C op with like arrows inverted. So big deal. We are not going there. So this is the code for Scala code for a diagram when we build diagrams in sets. So all the way, like in all further slides, I'll be talking about diagrams into sets. So a class diagram over the main category C, so C is like where we have those small c, b, and d, is a functor. So we provide the tag. Probably we had to provide the tag here too. So like a diagram has a name for printing. What do we have there? Like it's a functor, right? But because we have sets over there, here we have finite sets. Okay, so we can define that one diagram is a subdiagram of another. When one diagram is a subdiagram of another, if for every object, for every like position, for every moment, the diagram on the left is a subset, well, the value on the left is a subset on the right. So in this case, if it's an inclusion and f is a subset of g, fc is a subset of gc, fd is a subset of gd, fb is a subset of gb, then the whole thing is a subdiagram of this diagram. Also, again, we are talking about totally untyped sets, so like anything could be an element of anything else. So this is like a diagram is actually an element, a point in another diagram. That's where for every object in the second diagram, that second diagram, we belong to that other diagram. This diagram belongs to that other diagram if point-wise, like for every element, we are an element of that other diagram. So other diagram contains our value. So we extend set theory into diagrams. In sets, we had like subset. We had this like is an element. Now we can extend it for diagrams because we can define it just point-wise. So that's easy. We can like deal with bigger sets. Here's an example of diagram that is pretty popular. It's called TLA plus. And TLA plus is about diagrams in sets over the category of natural numbers. So what does a functor from n to sets consist of? Understand? No. It consists of sets indexed by natural numbers and functions from like one to the next. And the other functions, just because we need the functor, so other functions are just compositions. We cannot have anything else. So that's it. Is it mine? Oops. It says I have to go home. So the main category represents some kind of view of time, like time 0, like creation time, time 1, like the first day or whatever. And we have sets that are changing with time. And this is exactly a diagram over natural numbers. So I believe the whole book is the study of these diagrams, of this specific topos. Grothendieck topos. So this is the first example, and I'll be like mentioning domain as if it's some kind of time. It's not like, well, what is time? I don't know. I'm not a physicist. I don't know what's the nature of time, but maybe some people do. But we can always like model and talk about like things as if it's time. So we can view diagrams as sets that are dependent on those like background times. So one is TLA plus, when the time is 0, 1, 2, and so on, natural numbers. Another one is just sets, like no time, just one moment in time. A single transition when we have 2 moments of time, yesterday and today, or like today or tomorrow, depending on how optimistic we are. And we have 2 sets, like before and after, and the transition. I believe James Douglas was talking about this just like at 2 p.m. Today with these transitions. So this is like something like Git merge, right? So we have one branch, we have another branch, and transitions, and what we produce is something like this. So they come from 2 totally independent like times, and they could be really different times because like one person is in like Madrid, another in like Scotts Valley, California, and we want to merge them. And the thing is, the clock could be like very different, right? So this operation, that's what we do if we represent time like this. And this is something like eventual consistency. So we start with this, produce this, we start with this, produce this, but eventually we produce something that is compatible. So this transition is compatible with this transition. So like it's Git merge without conflicts. And we can think about these things as time again. And this is, I believe like last year I was talking about Groundhog Day diagram, but then it looked different. So this is like the category where we have, I don't know, hello? So, where we have February 1st, and then February 2nd like repeats forever, but it's just one arrow. So the composition is still the same. It's not when what's his name, whatever. So learn something, but anyway. And then there is a transition to February 3. So some people just fly through and they have no clue. The others like run and run and run like 2 years or something. So that's the diagram. How can we like represent it? How can we represent the logic of like dealing with this? How can we describe all possible combinations of like transitions, right? So we'll need a diagram. So for all these categories, we'll try to represent a diagram. But if we have sets like set here, set here, set here, and there are transformation like set of like people, whatever, that go here, some people go there, some people like roll and roll, and eventually go out or maybe never go out. So these are all sets, so we have to represent that thing. If we deal with a set, we know that sets consist of elements. And what's an element from categorical point of view? An element is what is known as point in category theory. It's an arrow from a terminal object to our, like whatever, our set. In diagrams, it's a little bit more complicated, not much. So we have a terminal diagram. What's a terminal diagram? A singleton on every like moment of time. And in an arbitrary diagram, we need like an arrow from here to here. So we need just to specify an an element in each specific set. Like here we have a diagram D with transitions, and we need to specify a point here, and point here, and they should be compatible. Otherwise, like it's not an arrow. It's a natural transformation, right? So a natural transformation should be compatible. So that's all that we need for a point, except that unlike sets, in diagrams, things don't all consist of points. Imagine like this part is empty, or this part is empty. So there's no point there. So we can have like partial points. I'm not going into partial points, but just keep in mind, some objects just don't consist of points. If we have a category that where all objects can be built out of points, the category is called well-pointed. But here, generally speaking, the category of diagrams is not well-pointed. Sets is well-pointed. So a point is defined in Scala code as like this. We have a tag, like give it a name, and a mapping. And a mapping is for every object in domain, we provide a transition. So where do we go? Yeah.
I'm curious why you would define that as a natural transformation.
See, a diagram is a functor.
Yeah.
So a transition from like an arrow from one diagram to another is a natural transformation. So generally speaking, like a point is an arrow from 1 to D. But why I didn't define it? Yeah, well, for like kind of cutting corners a little bit. Yeah, it is a natural transformation. And actually, I have a method that, like, given a point with this just like simple mapping, like for every object C, B, or whatever, provides something like here. Builds an actual natural transformation. Yeah, but to like manipulate, I have this like cheap solution. So it's a shortcut. Yeah, you're right. So now a topos, like I was talking about toposes already, the category of diagrams or the category of presheaves or whatever. A topos is a category that has finite limits, exponentials, and a subobject classifier. I'll like cover it a little bit. Finite limits is what? Like Cartesian products and equalizers. So you can probably look them up, equalizers or like pullbacks, whatever. So once you have it, that's what it means you have finite limits. Oh, and a point, a terminal object. If you have exponentials, and finite limits, and probably subobject classifier, you can build colimits as well, like all those unions and factor objects. But I won't focus on exponentials in this like discussion. We don't need it. But subobject classifier, I'll cover it right away. So here's an example. Given any category C, a category of diagrams over C, set to the power of C, is it not just a topos, it's a Grothendieck topos. Grothendieck topos is anything like this or a subtopos of this. So a category of presheaves over C, that's C op, right? And op should be up there, but okay. So is also a Grothendieck topos. It's a little bit more generic than just like set to the power of C, but we're not going there. It's almost there, yeah.
Diagrams have to be faithful.
No, anything, absolutely. All possible diagrams. Well, because like take, like, I don't know, take like this. So no, like preservation of any, no, absolutely not. Like, no, we probably have to talk about parallel pair, right? Like, if we have a diagram of a parallel pair, so should the like mappings of A and B be distinct? No requirement, no. Even like A 0 and 1 can map like to one single object, like constant functor, right? It's also a So what's an omega? What's a subobject classifier? A subobject classifier is a special object in our category, like, or in our topos, with mapping with a point called true, an arrow from 1 to omega. And you see that like dovetail or whatever, it means that it's a monomorphism. And why is it a monomorphism? Any arrow from 1 is a monomorphism. So such that for every pair like object x and subobject x1, there's a characteristic arrow from x to omega such that the whole thing is a pullback. So x1 can be retrieved by having this characteristic arrow. So you know how it is for sets, right? So in sets, omega is true and false, this pair. And so if we have a set and subset, so that characteristic function would be producing like true on x1 and false on those things that are not x1. If we have a more sophisticated category, it could be like more complicated, the omega. So the question is in diagrams, how do we build subobject classifier in diagrams? Well, there is a solution. So this is the solution. We build, like this is an object inside topos. So this is a special kind of diagram called omega, and this means that we build it like on the specific topos. And the domain, domain is probably set, no, this, yeah, whatever. Domain is the category on which it's being built. So I'm not like providing all the code here, but to build an omega, we need representables. And what is a representable? A representable functor, like in a category, like given a category C, not in sets, but in category C. A representable functor is for an object X is just a home and a set or whatever, like collection of all arrows from X to Y. So that's it. Given an X, we produce, we have this representable functor that consists of these things, like arrows from X to Y. So that's why a representable is defined like this. It's a diagram from called home from X, we provide an X, right, to like whatever. And how do we build how do we build the value of this representable on on any Y? Because we need to build something on any Y. We just have a home. We list all arrows from X to Y in that original set category, like category C. So for instance, if we go back to this category, right? So representable on 0 consists of, well, it's a functor, right? So we have to define representable of 0 on 0 and 1. On 0, it consists only of the identity on 0. Yeah?
So this representable is a functor that maps an object to
set.
Setmorphism.
Yeah.
With that object as a source. As a target, right. So it would map 0 to the set of morphism with 0 as a target.
Well, it depends on how we look at it. So like, I'm kind of like making it cheaper, so like representable from.
From, okay.
Yeah.
So it's,
yeah, so 0 is the main, but like the value, like H0, I cannot write it. So H0, on 0, it consists of arrows from 0 to 0. On 1, it consists of arrows from 0 to 1. Arrows from 0 to 0, there's just one arrow, which is identity of 0. On 1, we have A and B. So this functor for 0 consists of like one thing and then A and B. If we take H1, H1 consists of arrows from 1 to 0 and from 1 to 1. From 1 to 1, we have just one identity. From 1 to 0, there's no arrow. So that's it, empty there. So that's how it all builds. And now, we have Yoneda lemma. By Yoneda lemma, for any diagram, the value of that diagram on X is just a home in our like bigger category from consists of arrows from HX to that category. So okay, so we need to somehow build like for every given X, build the set of all possible arrows from HX to omega. How do we build it? But look at this definition. Every arrow from an object to omega is in one-to-one correspondence with subobject of that, with subobjects of X. So in our case, Hom from hx to omega is just equivalent, is in one-to-one correspondence with sub-representables, the subobjects of representables. So suppose like for this category parallel pair, right? So on the left we'll take like empty, and for h1 we take empty and that identity. On the right could be like empty, a, b, and ab. So that's how it is. So that's why we can easily build this thing, omega of x. So this is the code, the logic for the code. So like, yeah.
Sorry, I don't mean to be rude. But I guess I am curious about your nail down. So you have on the top line, you have hom from h sub x to omega, right?
Well, so, yeah.
Hom of x is a function for h sub x.
Oh, see, there are like different homs in different categories. On top, we have hom in category C, in that our small category, on the domain category. So we have like in a parallel pair, we have just two non-trivial arrows. Below, we are talking about hom in our topos, in the category of diagrams. So omega on x consists of, is equivalent to the set of all possible natural transformations from hx to omega.
Right, where omega, right, in the hom is the identity natural transformation, right? Because h sub x is a function.
Oh, no.
So in order to have a natural transformation.
No, see, like, say, let's. We have like in this set to the power of c, so that's where we are, right? So now omega is a diagram that is a functor. Hx is a functor, representable functor. And so that's how it is. Like we define omega like A, like B, omega D, omega on C. So these arrows are defined like kind of in a pretty trivial way. But how do we build these things? We build these things by the fact, by Yoneda lemma, we have this, and now this is actually, well, it's not like equal, it's like more or less in one-to-one correspondence. And this is in one-to-one correspondence with what? Arrows from representable to omega. Well, because of this property of omega. We can say like P. All arrows from representable to omega are in one-to-one correspondence with subobjects of hx. And we build that representable, right? And we can list subobjects easily. Just list all those elements of the sets. No, list all subsets on each component and see which ones are compatible. So that's it. That's what we need to build it. And so when I build this, the omega also, like it consists of all those things, of all those subobjects of representables, like on each component, but also we provide false and true.
So does every topos have a false and a true? I mean, it may have other.
Well, no, false and true. False and true. They are two arrows from terminal, but they're defined component-wise, right?
Thinking about like the very first topos you gave, where it was eventually became true. There didn't seem to. I mean, there was a false that you didn't.
The false is like we'll never get there. So if we talk about n, right? So this like TLA plus, right? So we'll have false that we'll never get inside, right? And we have true that we are always there. And there are things that like tomorrow, like 2 days later, and so on. And there's like an infinity of those possible points. possible value.
There are always at least two.
Yeah. Mm-hmm. And I have this like cheap enumeration of points, like list of all possible points in omega. And why do I have it? Because I sort the points by the size. So of course that there are like better ways to find truth and false, but this is the cheap way. Like I'm a programmer, not a mathematician. So the cheap way, just I have them and take the last one, and we call it, the last one is true because that's the biggest one, and the first one is false because that's like empty everywhere. So it represents empty sets, well, because we have like all sets component-wise, so it represents empties. So that's what is false for. So again, like what is Grothendieck topos? Consists of diagrams as objects. It's a category with diagrams as objects, and natural transformations of diagrams as arrows. So that's how we define it. And topos is just an abstraction about like what do we have there. So I don't think it has any implementations. So in Grothendieck topos we have a domain. We have an object omega. Well, because we know how to build it. Generally speaking, topos has a subobject classifier, but it doesn't provide us with any like rule how to build it. In Grothendieck topos we know how to build it. Also, I had to define it. It's actually a lazy val, like omega cross omega. It's a Cartesian product of omega with itself, and there are like other things that are provided for calculations. So why do we need omega cross omega? Because we have logic now. We can define binary operations, right? So that's the logic we defined on that object omega. So we have false, which is just the first possible point, and true, which is the biggest point in omega. And we have conjunction operation. It's from omega cross omega to omega. Oh, well, conjunction, well, all these operations are defined on subobject classifier. And they represent the idea of like conjunction. It represents an intersection of two diagrams, like two subdiagrams in a diagram. Disjunction, it represents a union of two subdiagrams in a diagram. Implication represents something like the idea of one subdiagram being a subdiagram of another subdiagram. So we have this omega, and we need to provide something like more operations. One specific operation is diagonal. It's from omega to omega cross omega. So you know how it is, like take anything and take a pair of that. So if we could draw that. If we could draw like omega here, omega there, so diagonal would be like this. So that's an inclusion of omega into its square. And it's traditionally denoted as diagonal. So that's what we build. And why do we need it? Because we can define these operations through classifications and through these tricks. Like here's how conjunction is defined. Conjunction is defined like this. Given a diagonal, a mapping into omega cross omega produce a conjunction. So basically the result is like how much the first one is equal to the second. Meaning that it like extracts, if we talk about the intersection of two like diagrams, two sets, we are talking about like what's in common between them. So how close they are. So classifier of diagonal, that's the very generic definition of conjunction that works like in any intuitionistic logic. This is not like bound to Grothendieck topology. It's just a general definition of conjunction in any intuitionism, because intuitionism and topos theory are like kind of synonyms. So that's how conjunction is built. I will not show disjunction because it's tricky. It uses power and whatever, but I'll show you implication. So what is an implication? It's about like how one thing like is smaller than another, how the degree at which one thing is part of the other three. For that, we need to build a partial order on subobject classifier. And then we classify this partial order, and omega 1, in a sense, yeah.
Or just the wrap in the next few minutes.
Yeah, I'm close. So represents pairs like A that is less than B, A that implies B, right? How do we build it? Well, you know how implication can be defined. If we take the first, like we take A and B, and we take only those that A conjunction B is equal to A. So that's how it is, like intersection of set A with set B is equal to set A. So that's how we define partial order, special like set or diagram of pairs, and then we classify it. That's inclusion. So this is the actual Scala code, inclusion of omega 1 into omega. And I hope mean that the inclusion actually may not produce a result. So it produces my class result, which I'm going to switch to IO to 0. And so I hope it get the result or just throw as an exception. So that's how it is. And we have an inclusion and we have characteristic function of inclusion named like this. So predicate, like given a point, we can build a predicate, which is what? Which is a diagram arrow from a diagram to omega. So given a point P, we have this predicate. It just produces the values of, produces true on those things that are inside this point. So given a point, we produce a predicate, and we build that predicate for this. So a predicate, this arrow from D to omega. Well, that's what a predicate is, right? An arrow to classifier. The thing that classifies our point. So for predicates, we can define, like, given one predicate and another, conjunction, disjunction, and implication. I had to use this because, like, I couldn't use the standard notation from Scala, even, unfortunately. And negation is exactly defined as P arrow false predicate. And false predicate is something that a constant predicate that returns false all the time. So this is how the tests look like for this code. So we check that true arrow P is equal to P. And I check it on a bunch of categories that I showed in the beginning. And this, like, false always true, and P arrow P is always true, and so on. Triple negation is the same as negation, and all these things, like, how they call it. So what we had, like, categories, big sets, diagrams, and points, and Grothendieck topos, and these operations. And, like, the thing that I'm proud mostly is the collection of unit tests for that. Well, because I was really tired. So tired of Scala. So I don't know, like, quoting Tony Morris about Scala. If you are signed up for his tweets, so that's how it is. And eventually I got the feeling that, am I dealing with Perl? Am I writing in Perl? Every time I have to figure out, like, what type do we have? Like, transforming, like, a composition as instance of, and so on. So this is, like, the dirty corners which are being hidden by, like, nice API which like looks good in the tests. So that's life, right? But this is how, like, tests look like. So pretty readable, right? So we have a representable, and we check that that representable, like, on this object produces this, and so on. So the tests look like the kind of the level of perfection that I respect, but not the actual production code. So we have, like, a representable, and we build so this is a builder of representables. So, like, we take representables on all possible objects and we produce this. So that's how tests look like. And these are references, including, like, an amazing talk by Francois today. And so this is the thing about topos theory. This is not an introduction to topos theory. This is just a discussion of topos theory and its like mentality. This is also, like, a nice reading, and these are technical things, and these are the books to read. And thank you. Do you have time for questions now? I don't know. By the way, the link is here. So, oh, sorry. Lambda 19 CILC, calculating intuitionistic logic in Scala. And the last slide is about actually subobject classifier for the groundhog thing. That's how it looks like. Thank you.